Hello everyone, this is Professor Roman. Welcome to the 13th video in my video lecture series on Introduction to Discrete Mathematics. I need to correct something from the last video. It's entirely my fault. In the definition of Boolean polynomial, I forgot to say that a Boolean polynomial is a compound statement that involves only, it's not what I had in mind, only conjunctions, disjunctions, and negations. No conditional and no biconditional connectives. The examples follow that. And everything I did follows that. I just forgot to include that in the definition. That's my fault. I also want to elaborate just a touch on a result that we discussed last time. Every truth table is the truth table of a Boolean polynomial in disjunctive normal form. I've placed that sentence, which was in italics and indented, into a theorem so I could refer to it later. And I also added a bit of terminology. We will say that such a Boolean polynomial represents the truth table if the truth table of the Boolean polynomial is that truth table. Another thing that I wanted to discuss before we move on to logic circuits, actually I started to do the logic circuits video and I realized there's some other things that I should discuss first that actually do bear relevance to logic circuits. And that is adequate sets of connectives. Now, frankly, it's not so easy to find a clear definition of the term connective. I didn't give you a definition earlier. I simply said there are 5 basic connectives: negation, conjunction, disjunction, conditional, and biconditional. I poked around in the books I have in my library and on the internet and didn't have a whole lot of luck finding a good definition. And perhaps the reason is that it's not that important. I don't know. But here is a definition. A connective is a formal symbol that has one or more inputs and a single output, as well as a truth table that describes the possible outputs based on the various inputs. Generally, connectives have very few inputs, 1 or 2 usually. And the connectives, the 5 basic connectives we've discussed, fit this definition. So do other things, and I'm going to give you 2 more connectives a bit later in this lecture. There are only 4 one-input connectives, 3 of which are quite boring. Tautology, which always returns true based on for whatever the input is. Contradiction, which always returns false. Negation, which, as you know, is important. And what we might call identity, which simply returns the value of the variable. There are 16 possible 2-input connectives, 1 for each of the 16 possible truth tables with 2 variables. And we're familiar already with conjunction, disjunction, conditional, and biconditional. And as I said, I'm going to add 2 more to this list, and 2 more that have important applications. The intent of a connective, of course, is to connect logical statements together to build larger logical or compound statements. And here is the definition of a compound statement that applies to any set of connectives, not just the 5 basic connectives. So let V be a set of statement variables and let S be a set of connectives. A compound S statement, or simply an S statement, is defined as follows. This is done inductively. All statement variables are S statements, generally called simple statements. If A and B are S statements, then so is A sigma B with parentheses, where sigma is a connective. And then we have the usual limiting clause. I have not seen this sort of definition elsewhere, and the notion of an S statement, so you may or may not see it elsewhere, but it doesn't matter. It's going to be useful to us in this video. And so now we're ready for the main point here, except for one more definition. A set S of connectives is adequate if for any truth table T, script T, there is an S statement whose truth table is T. Theorem 127 tells us that this set that contains negation, conjunction, and disjunction is an adequate set of connectives because any truth table can be represented by a Boolean polynomial in disjunctive normal form, and those are S statements because they involve only negation, disjunction, and conjunction. Or I guess I should have said conjunction and disjunction. The question is, do we really need all three of these connectives? De Morgan's laws tell us, in fact, we do not. For example, a min-term, which is part of Boolean polynomial in disjunctive normal form, they're disjunctions of min-terms. A min-term, which is a conjunction, is logically equivalent to this. It's De Morgan's law. And this only involves negation and disjunction. So it's a statement over these two connectives. So any Boolean polynomial in disjunctive normal form is logically equivalent to a statement that involves only disjunction and negation. We've eliminated conjunction. And we haven't lost anything because we still get all the truth tables that we got before, which is all the truth tables. Similarly, we could do without disjunction if we keep negation and conjunction, and that's clear from conjunctive normal form. So both of these sets are adequate. And I'm going to leave it to you to show that this set, negation and implication, is also adequate. Showing that a set of connectives, say S, is not adequate can be quite a bit more challenging than showing that it is adequate. The key to this is to find a truth table, or a piece of a truth table at least, that is not the truth table of any S statement. So consider, for example, this set of connectives. This is all the 5 basic connectives except negation. If this set was adequate, it would be possible to construct an S statement that returns false when every statement variable is true. So it would be possible to construct an S statement where this row, or this was a row in a truth table of an S statement. Well, simple S statements, which are statement variables, obviously evaluate to true when the variables are true. All I said was P is true when P is true. So we have to keep a keen eye on this definition. What we're trying to show is that all S statements have or in fact do not have, a certain property. We do that by showing that all statement variables have that property. And then we show that if A and B have the property, A sigma B also has the property, which will mean all of the statements have the property. So far we've just dealt with the simple statements, which are the statement variables. Now we can assume that A and B are S statements that evaluate to true when all the variables are true. Well, then so will all of these. And so it follows that all S statements evaluate to true when all variables are set to true. That shouldn't be entirely surprising. Without negation, if all the variables are true, we have no way to, well, negate a variable. So this means that no S statement will produce this row in any truth table. So all you have to do is form a truth table with this row, and you can say that no S statement represents that truth table. And therefore, this set of connectives is not adequate. Nor is any subset of this set, because any subset of a set that's not adequate is also not adequate. So in order for any subset of the 5 basic connectives to be adequate, the subset has to contain negation, and then it only needs to contain one other of conjunction, disjunction, or implication. What about this set of connectives, negation and biconditional? This is a tricky one. So I'm going to go through an argument. I have not seen a discussion of this in any of the books I have. It's not that many, maybe half a dozen, that relate to this subject. Nor have I seen anything on the internet. So maybe nobody cares, but we're going to go through it anyway. The key to the argument we're going to use is that a biconditional, A if and only if B, tracks only the truth-value relationship between A and B. It tracks only sameness, the sameness of the truth values. If A and B have the same truth value, this is true, otherwise it's false. And that's the key. Now, to simplify the discussion, I'm going to introduce some terminology that I just made up for this purpose, so you won't see it elsewhere. Suppose that a statement A contains a variable P. Then I'm going to say that A tracks P if a change in the truth value of P always changes the truth value of A. So if P is true and you switch it to false, whatever A was, true or false, it switches truth value. So I'm not saying that A and P have the same truth value, just that they change at the same time. They switch truth values at the same time. On the other hand, if a change in the truth value of P makes no difference to the truth value of A, this is regardless of any other variables and what their value is. Then I'm going to say that A is oblivious to P. Okay. Now, note that disjunction, P or Q, neither tracks P nor is oblivious to P. So there are other alternatives. Because in this case, changing the truth value of P will have no bearing on the statement P or Q, when Q is true. When Q is true, the disjunction is true, P doesn't matter. But when Q is false, then P will determine the truth value. Okay, so P or Q does not track P. It doesn't always change with P, and it's not oblivious to P. It doesn't always ignore the value of P. So the plan, just as we did with the previous example of a set of connectives, is to show that the S statements that come from this set of connectives always either track a variable or are oblivious to a variable. And then we will know that no S statement can duplicate the truth values or the truth table of disjunction, and therefore this set is not adequate. Okay. So we start with statement variables. A statement variable P tracks itself. It changes when P changes. After applying one iteration in the inductive definition of an S statement, we will have either not P, P implies a P if and only if P, or P if and only if Q. Q is a different variable from P. Now, P if and only if P is a tautology. It's always true, so it's oblivious to P. Not P tracks P. When P changes, not P changes. P implies Q tracks P, because when P changes, then the sameness between P and Q changes. If both of them were true and you change P, then they're not the same anymore. One's false and one's true. Okay, so sameness is tracked here. Okay, so let me say that again to be absolutely clear. Think about the truth table for P if and only if Q. All 4 rows. If you change P, you will change P if and only if Q, regardless of whether Q was true or false. Okay? You might want to write the truth table down and think about that. Now we can assume that we have 2 S statements, A and B, that either track or are oblivious to P, and we want to go to the next iteration in the definition of S statement. That will give us either not A if and only if A, or A if and only if B. We now have some cases to consider. Okay. Each of A and B separately either track P or are oblivious to P, don't care what P is. And we need to show that the same is true for these statements. Well, if A is oblivious to P, so is not A, right? If changing the value of P doesn't change the value of A, and when I say value, I mean truth value, then the same thing applies to not A. And if A tracks P, then so does not A. So this one is easy. This one's even easier. It's a tautology, so it's oblivious to P, to anything. Frankly, it's always true. The last one also has to be broken down into cases. If both A and B are oblivious to P, in other words, they don't change value when P changes, then this is certainly not going to change value. If A is oblivious to P, it doesn't change value when P changes, but B tracks P, it switches value when P switches value, then a change in P changes only B and not A, so it changes the sameness of truth value of A and B. If they were the same, they become different. If they were different, they become the same. And so this truth value will change. And so A if and only if B tracks P. Now the same kind of argument will hold if it's A is the one that tracks and B is the one that's oblivious. A and B play a symmetric role here, so it doesn't matter. Finally, if both A and B track P, then sameness is not affected by a change in P, okay? Because A and B, both of them change. So if they were the same, they're still the same. If they were different, they're still different. And so A if and only if B is oblivious to P. So as promised, all S statements either track P or are oblivious to P for any statement variable P. But as I've already discussed, disjunction is not either oblivious or tracks P. Half the time it tracks P, the other half the time it doesn't, depending on the value of Q. So no S statement is logically equivalent to disjunction, and so S is not adequate. That's a lot of work. Maybe there's a simpler way to do this. This is just what occurred to me, and so I wrote it up. So in summary, these three sets are adequate. These two sets are not adequate, and therefore any subset of these two sets is not adequate. Well, what remains? How about a single connective? It's not going to be one of these three, and it's not going to be this one. Okay. Could negation by itself be adequate? Not hardly, and I'll leave that for you to sort out. So none of the 5 basic connectives alone are adequate, but there are other connectives besides the 5 basic ones. And there are 2 of those that are adequate by themselves. The Sheffer-Stroke is the connective of 2 variables denoted by an arrow pointing up or just a vertical bar, and this is the truth table. It's false if both P and Q are true, otherwise it's true. This connective was named after Henry Sheffer, who introduced it in a paper he wrote in 1913. The truth table for the Sheffer-Stroke is the same as the truth table for not P and Q. And so the Sheffer-Stroke is also referred to by the acronym NAND for not and, because that's what it is, not and. And we have these equivalences. Now, not P is equivalent to not P and P, and that, by this line here, is equivalent to P stroke P. So the Sheffer-Stroke gives us negation quite easily. P or Q is equivalent by De Morgan's law to this, which is equivalent to this Sheffer-Stroke, which is equivalent to this. So the Sheffer-Stroke also gives us disjunction. And because these 2 connectives are adequate, so is the Sheffer-Stroke. So in short, we can produce any truth table we want using only the Sheffer-Stroke, NAND, not AND. It's quite a powerful connective. The other single connective that forms an adequate set of connectives is called a Pierce arrow. And the Pierce arrow is denoted with an arrow pointing down. It is logically equivalent to not P or Q, in other words, nor. Here's the truth table, and I'm leaving this one for you to show that it is adequate. Okay, so you might be thinking all this was just technical, theoretical stuff of no practical value. That's not quite the case. When we start talking about logic circuits, which we will do next, we will discover that most simple logic circuits are made up of three what are called gates: AND gates, OR gates, and NOT gates, or inverters. So an AND gate has two inputs, and it takes their conjunction, and so on. We'll talk about that. But something called the Apollo Guidance Computer, which was a digital computer that was produced for the Apollo program, was actually constructed using only NOR gates. No AND gates, no OR gates, no inverters, just NOR gates. So the fact that the NOR gate, the Pierce arrow, is adequate told the Apollo folks that they could construct anything they needed to construct using just NOR gates. Well, I think that's probably enough for this video. I was going to continue it and discuss logic circuits, but this has already run almost a half an hour, and that's probably what I have to say about logic circuits, and I don't want the lecture to run too long. So we'll stop it here. We'll do logic circuits in the next lecture. Thank you for watching, and I hope to see you in the next lecture.